So today's topic is force. This is the first chapter of your physics book. So can anyone tell me what is a force?
External physical cause.
External physical cause. All right. This is something that you must have learned in class 8, the way to define force.
Push or pull of a body.
Yeah. All right. The push or pull that is exerted on a body. So here you can see in the picture I've shown you that we have push, pull, and then we have magnetic force, gravitational force, frictional force, acceleration, and so on and so forth. This is something that you have done in class 8, 9. All right, but in class 10, we'll be learning something little bit more interesting. So first of all, let's start with the topic types of motion. All right. So to understand this, let's take an example. Let's say that we have a ceiling fan, all right, under which there are some kids, it's very hot and they are enjoying the cold air of the fan. All right, so the fan will be hinged at a point. Yes or no? The fan will be connected at a point. So this point where the fan is connected is known as the pivot or the fulcrum. All right, and if you want to rotate the fan, what would we need? Yes, Abigail, we will need a force. So let's say you applied a force in this direction. All right, obviously the motor will apply the force, but here imagine that you're applying the force yourself. So if you apply the force, then of course the fan will start rotating. All right, so what is the fan doing? The fan is rotating about its axis, right? So this is the axis at which it is rotating. It is an imaginary line about which the fan is rotating. This is known as the turning effect of force. So whenever a force produces a rotational motion, right, or rotating body, it is known as the turning effect of a force, and the motion itself is known as rotational motion, right? Rotational because it is rotating, right? Okay. So another example can be, let's say, a wheel. You can see that is the wheel of a bicycle that is rotating. So that is also rotational motion. And look at this, people playing seesaw. All right. So here you can see that the seesaw is also rotating. So that is also an example of rotational motion. So for rotational motion, what is the most important thing we need? What do we need? We need a force, and very important is the pivot. All right, the pivot point at which it will rotate. So what if, let's say we have the fan, but we don't have a pivot. All right, the fan is not connected anywhere. And now if you apply a force, what do you think will happen to the fan? Will it rotate? No, because it doesn't have a axis of rotation. So what will happen? The fan will fall on your head. Now what happened? See, the fan fell like this. This type of motion is known as translational motion or linear motion. So there are two types of motion: rotational motion and linear or translational motion. For example, this car, look at this car, it's moving in a straight line. So if the car is moving in a straight line, what kind of motion will it possess? Linear or translational motion. Is the car pivoted at any point? No, the car is free to move, and hence it is producing translational motion. You got the two types of motion? Okay. Now I'll ask you a very interesting question. Let's see if anyone can answer. Focus on the wheels of the car. All right, focus on the wheels of the car. What kind of motion do you think that is? Rotational motion, okay. Everyone is saying rotational motion. Anyone, any votes for linear motion? No? Isn't the car moving? Isn't the wheels of the car moving in a straight line? Look at this, the wheel. Yes, the wheel is rotating, so there will be rotational motion, but the wheel itself is also moving from one place to another. So is there linear motion or not?
Yes.
Yes. So there is linear motion as well as rotational. That means both is also possible. Sometimes students get confused that, oh, rotational, so it must not be linear. But there are many examples where it can be both. Okay. Another example can be, let's say, for those who play football. If you kick a ball and the ball is moving, but at the same time the ball is spinning. So rotational motion because it's spinning, but it's moving from one place to another. So translational motion as well. All right. Okay. So what causes this rotational motion is torque. Let's understand what is torque. So torque, or it's also known as the moment of force, is a measure of rotational force that causes an object to rotate. Okay, in simple word, torque is something that causes the rotation. All right, we have a definite name for it. So we can call it cause or moment of force. Let's understand this with an example. What is this guy trying to do? He's trying to unscrew the bolt that is under it. Yes or no? So to unscrew, he's using a wrench, right? So when he uses the wrench, why is he using the wrench? So that he can produce torque, right? That rotational motion he wants to bring, so that's why he's using a wrench. But now my question is, how do you think, on what do you think this torque depends? Very good. One will be the force. More force he applies, more will be the torque, right? So first thing will be the force. What about another one? Yes, it also depends upon the distance between the pivot and the point of application of force, means where he is applying the force. Based on these two, the torque will depend. So we get torque is equal to force into perpendicular distance. Notice here how I'm writing perpendicular, not just any distance, because the perpendicular distance means it always has to be the shortest possible distance. Is it fine? Okay. So can you figure out what will be its SI unit? Yes, because force, the SI unit is Newton, and perpendicular distance, basically distance, its SI unit is meter. So the SI unit will be Newton meter. But what will be its CGS unit? Yes, very good, because force is measured in dyne and perpendicular distance is measured in centimeter. So the CGS unit will be dyne centimeter. Let's try to connect them both. All right. Let's say if we take 1 Newton meter, how much will it be in dyne centimeter? So see, 1 Newton meter, how did I get? 1 Newton meter I got by multiplying 1 Newton into 1 meter. Now 1 Newton is how many dynes? 10 to the power 5 dyne. Very good. And 1 meter is how many centimeter? 100, or we can simply write 10 to the power 2 centimeter. So if you multiply 10 to the power 5 times 10 to the power 2, we get 10 to the power 7 dyne centimeter. So that means 1 Newton meter equals 10 to the power 7 dyne centimeter. Please note this down. So, I said that this perpendicular force is very important, all right, because a lot of times students get tricked by the perpendicular force. Okay, let's see if you will get tricked or not. So I'm going to show you an image here. That's the image of a bicycle pedal. All right, the half of bicycle pedal. And let's say you're riding the bicycle. So with your feet, you're applying the force in the downward direction as shown in the arrow, right? And the length of the bicycle pedal is, let's say, 17 centimeter. Okay, so roughly this much. My question is, what is the perpendicular distance here? Or to be more precise, is it 17 centimeter? Very good. I can see some nodding of head. Elizabeth? Yes. Okay. Your friend is saying no though. Okay, let's see. What about others? Yes or no? Yes, Mary? Okay. Zishan? No. All right. See, this is the direction of the force and this is the distance that we are measuring. So this is 17 centimeter and this is the force 30 Newton. Look at this. Is the distance perpendicular to the force? Is this angle 90 degree in any way? No. So the distance is clearly not perpendicular. All right. So if you're saying 17 is the perpendicular distance, it will be wrong. Then which distance will be the correct one? It will be this distance from here to here. All right. This distance. Let's say this distance is 4. So this distance will be the perpendicular distance. All right. So for example, if I measure this distance, now look at this. Is this perpendicular? Yes or no? Yes. So 4 centimeter, if you said, it's correct because the force and the distance must always make an angle of 90 degree. All right. So a quick revision. Then what will be the torque here? What is the formula of torque? Force. Very good. Force into perpendicular distance. What is the force? 30 Newton. What is the perpendicular distance? 4 centimeter. So it will be 30 into 4, 120 Newton centimeter. Not meter, Zishan. Because we're using the perpendicular distance, we are measuring it in centimeter. So it will be Newton centimeter. Okay. Alright. So let's see the next one, that is direction of torque. Alright, now this torque has two direction. First one is anti-clockwise or counterclockwise and the other one is clockwise. Okay, a very simple example like let's say I have this marker and it is pivoted at this point. Okay, now tell me from your perspective, if I push it here, will it rotate clockwise or counterclockwise from your perspective? Counterclockwise. Okay, but if I push it from here, it will be clockwise. So that's the meaning of direction of rotation or direction of torque. All right. So by definition or by convention, we take the counterclockwise as positive and clockwise as negative. Okay, this is a standard you will have to remember. Okay, it will be useful when we do the numericals. All right. So how can we change the direction of torque? Okay, one I have already showed you. All right, let's say this is a pen. If I push it from here, you said it's going to rotate counterclockwise. How can I make it rotate clockwise? By changing in, yes? By changing in position. That is here. Here? Yes. See, if I push it here, won't it rotate clockwise now? That means one way to change the direction of torque is by changing the point of application. Very good, Abigail. What about another one? Very good, changing the direction of force. Let's say I want to push it at this point only. Now, if I push it this way, counterclockwise, but I want to push it this side only, so I can push it from down now. Now I've changed the direction of force. It's this way now. So now it's rotating in the other way around. Yes or no? So I can either change the point of application or I can change the direction of force. Okay. So you have already answered. So look at this animation. Okay, he's opening the door. So which way did the torque move? When he opens the door, it will be this way. So it will be counterclockwise. And when he closes the door, it will be clockwise. But look at, did he change the point of application? In both the cases, where is he applying the force? On the doorknob. But look at the direction of force. When he closes, he is pushing. But when he opens, he is pulling. So is the direction of force changed or not? That changes the direction of rotation. But the other way is by changing the point of application. So look at this image. When he applies the force on this side, maybe the force is down only, it will rotate this way, so counterclockwise. But when he puts the spanner in this manner, he's changing the point of application, force is still down, so now it will be clockwise. So counterclockwise to clockwise by changing the point of application. So two ways, either you change the direction of the force or change the point of application. Okay, so let's take a small break and let's test your understanding. All right, so I have an image generated by ChatGPT, but tell me what is wrong with this image. Let's see if anyone can tell me. Sorry?
The door hinges on the wrong side.
The door hinges on the wrong side, as in?
Because you see the side way. It's supposed to be on the opposite side so they can.
Well, okay, I honestly I was expecting that answer, that you will say that the door knob or the hinge is on the other side, right? But it's not, right? The door will still open. If I do this, if I hold the doorknob and if I pull it, will the door open or not? Huh?
No.
No? It exactly. It will open, right? See, try to understand, Zishan. This is the hinge, right? And the knob is right here. So if I apply the force here, will I not be able to move the door like that?
Yes.
Yeah.
Everything more force.
Exactly. Very good. All right. So this is where you were supposed to focus. Okay. For those who do not understand, here's the hinge and here's the doorknob. If I pull it, the door will open this way, right? But I am reducing the perpendicular distance. So if I reduce the perpendicular distance, the force has to increase to produce the same amount of torque. All right. Okay. Very good. Let's see another one. So there's a man, all right, he went to a trip and then all of a sudden his tire got punctured. So he needs to replace the tire, but before doing so, he needs to open those screws, those bolt, right? But he saw that no matter how much force he's applying, he's not able to produce enough torque to open the bolt. What can he do?
Use his leg. Body weight.
Yeah, so that's what I'm saying. He used his all force, he stood up on the thing and then he pressed and still he's not able to. What can he do next? That is a good one.
The other action, other tool which has longer distance from the hand to the point.
Okay. Irene? He can change the position of the hand as in. See, look at him. He's already holding right at the corner. So if you mean like to go a little bit far, he cannot do so. Right? But DJ said the right thing. Did everyone follow? He can use a longer tool or maybe he can add an extension to that same tool. That way, what is he increasing? The perpendicular distance. And if he increases the perpendicular distance, the torque will increase and maybe he'll be able to open the bolt. Okay, fine? Good, DJ, you were right. So now, let's see the next one, couple. All right, okay. One person has to smile. No, DJ? You smiled very fast. That's weird. Okay, so what is couple? I'm asking a question that everyone knows the answer. What is a couple? Huh? A pair. Yes, Elizabeth? Who's that? You said? Abigail? Okay. It's a pair of two forces. All right. Let me make something very clear here. Torque alone cannot cause rotation. Okay. If there is only one torque, it cannot produce any kind of rotation. For it to rotate in real life, there has to be two forces. A single force cannot produce rotational motion. All right, I'll explain you in detail how it works, but for now let's understand this. So then what is a couple? So a couple is when there are two equal, opposite, parallel forces. So what are the three important words? Equal, opposite and parallel forces, they form a couple. All right. For example, this bottle. Okay. I try to open the bottle. Can I open? But I am applying torque, right? Yes or no? It's not enough to open. All right. But then how do we open the bottle? We hold it from two ends like this and then we rotate. Yes. So one of my finger is pushing it this way and one of my finger is pushing it towards me. So something like this. Yes. So this, do you see there are two forces, right, produced by each finger, and these two forces, they contribute to couple. Is it fine? Then what about in a door? How is it possible in a door that there are two forces? Actually, it is possible. Imagine that this is the action force that you apply on the knob, right? You apply the force on the knob and then you try to open. Then where's the reaction force? The reaction force is on the other side of the hinge. Okay. This side there will be a reaction force and these two will contribute and become couple. Is it fine? Okay. So another examples can be, let's say, in a driving wheel, right? We hold the driving wheel like this and then we turn like this. So if you want to rotate, let's say towards the right, okay, then if you want to rotate like this, then with this hand you have to push up and with this hand you have to pull down and then you will be able to rotate, right? That's why the forces have to be opposite, parallel and also equal. Okay, another example can be a key. No, like this you hold the key and then you rotate it like this. Yes or no? Can you give me one example that I haven't discussed? Very good. A tap. So this is the thing. A tap, same way. Yes or no? Alright. So let's try to understand the formula of couple by using your friend's example only. That is a tap. So if I have to simplify the diagram of a tap, I can just draw maybe a straight line and then here will be the pivot and we apply two forces, one this direction, so let's say this is F, and one in this direction, let's say F, because we know that the two forces have to be equal. Let's say this is at point A, this is at point B, and this is the point O about which the tap is going to rotate. So can you see there are two torques involved? Yes? Yes or no? So torque 1 will be, let's say, because of this force. So it will be force into the perpendicular distance. Now the force is F. What is the perpendicular distance? Perpendicular distance is always measured from the force to the pivot. So what will be the perpendicular distance? AO. Very good. And for the other one, torque 2 will be force into perpendicular distance. The force is equal, so F. What will be the perpendicular distance in this case? OB. Very good. So therefore, total torque will be equal to what? F into AO plus F into OB. If I take F common, I get AO plus OB. Now what is AO plus OB? AO plus OB is AB. So that means we can say again it's nothing but F into the perpendicular distance. So this total torque is actually known as moment of couple, and that's the formula of moment of couple.
So, what is a torque?
Torque is the turning effect of a force. Like, see, when you apply force on something, no, a lot of things can happen. All right, let me explain. For example, let's say I have this cloth. All right, if I apply force on this, see what is happening. Can you see what's happening? its shape is changing. So that is one effect of force. No, deforming. It is deformed, right? Another one can be, let's say I have this cap and I'm applying force, right? So that is another effect of force. Similarly, we have another effect of force where the force will cause some kind of rotation. So that effect that it produces is known as moment of torque. A moment of force, sorry, or torque. You got it? Okay. Yes? Okay. So, Mary, what will be the SI unit from the formula? Try to derive the SI unit of couple. Very good. Newton meter. Okay. So, anyone has any question at this point? Because I have one. Hopefully, mine and Ananya's question is same. Anyone has any question? My question is with the formula. What is the formula of torque?
And force in perpendicular
Force into perpendicular distance. And what is the formula of moment of couple? Force into perpendicular distance. Are the two formulas same? Yes? Do they represent the same thing? Yes? They don't. That's why you might get tricked. See, for a torque, when we say perpendicular distance, we mean the distance between what? The distance between the force and the pivot, right? When we say torque or moment of force, perpendicular distance means the distance between force and the pivot. But here in moment of couple, when we say perpendicular distance, it means what? Distance between the two forces. So there is no pivot involved in finding the perpendicular distance. Okay, very small difference, but you have to know what it is. So copy that down. All right. So let's move on to the next part, that is equilibrium. So what is equilibrium? Let's try to understand this with an example. Imagine there are two people, okay, who are sitting in a car and the car broke down. Right now they need to take it to the repairing person, and let's say the repairing person is 100 meters away. What should they do? Let's say the repairing person cannot come to you. Let's add another constraint. What would you do? Walk where?
put the car in neutral and push it.
Put the car in neutral and push it. Do you drive? That was a very specific answer. Yes, you would get out of the car and push it, right? Yes or no? Walk, where will you walk? Where will you come? You'll come home, leaving your car there. Ananya? It's fine. Achha. Yeah, nobody cares about your car, no? Achha. So, let's understand this with this picture. So yeah, the two friends got out and then they started pushing the car towards the mechanic. Are they doing something wrong? Huh?
They're going against.
Yeah, basically they are pushing against each other, right? Yes or no? So these are two people who didn't study physics. Because when a number of forces acting on a body produces no change in a state of motion, a state of rest or linear and rotational motion, this is known as equilibrium. That means the car is in equilibrium. This person is applying a 200 Newton force in this direction. This person is applying a 200 Newton force in the opposite direction. So they will cancel each other out. And what will be the sum of the forces? The sum of the forces will be 0. And the car will remain in the state of rest. So this is known as equilibrium. Okay. So equilibrium can be of many types. The first one is known as static equilibrium. So what is static equilibrium? When a number of forces acts on a body, alright, producing no change in the state of rest. That means the body must be in the state of rest, then that is known as static equilibrium. Let's understand this with an example. Imagine this is your book on the table. Is there any force acting on the book? Yes. What are the forces? Force of gravity, that is gravitational force, which will act in the downward direction. Any other force? The force exerted by the table, which will be in the upward direction, is known as reaction force, equal and opposite. So see, it's just like that car example. One person is trying to push it down and one person is trying to push it up. Their forces being equal, they cancel each other and the book remains in the state of rest. So the book is in static equilibrium. Okay. Another one. Let's say two people of the same weight, 400 Newton, 400 Newton, sitting at an equal distance from the pivot, that is 2 meter, 2 meter, right? First of all, tell me, what will be the torque produced by this person? 800 Newton meter. Can you tell me whether it will be positive or negative? Positive. Counterclockwise, so it will be positive. And what about the torque produced by this person? Positive or negative? Negative. Okay. So this is the anti-clockwise moment, clockwise moment, negative and positive. So if you add them, what do you get? Net torque will again be 0. This type of equilibrium is known as rotational equilibrium. Alright, this is a common jargon that is used in question paper. They will say, is this in rotational equilibrium? Then what do you have to do? You have to find the anti-clockwise moment, sorry, this should be clockwise moment, and then you have to add them both. If you get 0, then it is in rotational equilibrium. Alright, I'll explain you this in detail when we do the numerical. But this is one of my favorite, that is dynamic equilibrium. So what do you think it means by dynamic equilibrium? When the body is in the state of motion. Okay. So example, a raindrop. Okay. Now let's say this is the raindrop and the raindrop is falling, right? And it hits your head. Does it hurt? No, right? It's totally normal. But let's say it's a hailstorm, right? And that hit your head. Will it hurt? Yes. Let's try to understand why does the raindrop not hurt. Okay. So let's say the raindrop is falling. Alright. So as it initially falls, its velocity keeps on increasing. Right? What are the forces acting on the raindrop? Obviously gravitational force, because there must be a force that is pulling it downward, and very good, buoyant force from the air, which will be in the upward direction, given by rho gv. Alright, that detail is not important, but this buoyant force is a variable force. That means it increases with your velocity. So as the raindrop comes down, its velocity will increase and the buoyant force will also start to increase, right? After a point, the buoyant force will become equal to the gravitational force. So what will be the net force? 0. So that means it is under no forces, right? And it is still falling down. So it's in the state of motion. So this is an example of dynamic equilibrium, right? That basically means what? The raindrop, as it starts, its velocity will increase. But after a point when the buoyant force is equal to the gravitational force, its velocity will no longer increase and it will fall at the same speed. And it will hit your head and nothing will happen. Okay, but in case of hailstorm, the gravitational force will be more because it depends upon the mass. So gravitational force will be more, so it will take much longer for the buoyant force to become equal. That means its velocity will be higher than the raindrop. Okay, if the same thing had happened in, let's say, space where there is no air, so no buoyant force, so the force will keep on pulling the raindrop down and the velocity will keep on increasing. In that case, even if that raindrops fall in your head, it will be very painful. Alright? Okay. So this is the last topic for today. Before that, anyone has any question, please ask. Okay, since you don't have any question, let me ask you one. Can you give me another example of dynamic equilibrium? Means the net force should be zero, but the body is in motion. A car, okay, I like that. How? Okay, go ahead.
There is no actual net force, but still maintain the velocity.
There is no net force, but the velocity is still being maintained. Like how?
So I'm not explaining.
Okay, but that's a very good example. Okay, let's say that you are driving a car. Okay, let's say it's a straight highway. Okay, and you're driving a car. So initially, when you start the car, your velocity will be. When you just started the car, your velocity will be zero. And as you press the acceleration pedal, alright, your velocity will increase. So it will increase to 10, 20, 30, 40, 100, 200, 500, 1000, 2000, right? Yes? Yes? Yeah, so now I know how many of you are just nodding head. Will it reach 1000 car? Which car do you have? Will it reach 1000? No. What happens? 10, 20, 30, 40, 50, 60, 100, 200, 300, 400. But after that, even the fastest car cannot pick up the speed, right? Yes or no? Have you seen any car going with 1000 km per hour? Yes or no? So after that point, let's say beyond which your car cannot go any further, right? That time there are two forces acting on the car. One will be my drawing is very bad, okay? One will be obviously the driving force that is pushing the car forward, that is coming from the petrol, diesel, whatever you're burning, and one will be from the air resistance that is pushing your car behind, or frictional force, right? At a certain speed, depending upon the car, the force that is pushing it forward becomes equal to the sum of the forces that is pushing it behind. So they will cancel out. So the net force will be zero, but the car will still continue to move with the same velocity. Okay, very good. That's a good example of dynamic equilibrium. Then let's move on to the next topic, the last topic, that is principle of moment. So imagine that we have a pan balance. Alright, again, this is also generated by ChatGPT, so don't ask me why this is so big and this is so small. Okay, ChatGPT made it easy for me to explain. So on this side we have a heavier mass, right? Let's say that it's exerting a force of F1, alright, at a distance of D1 from the pivot. Okay, let's say we have another mass F2 at a distance of D2 from the pivot. Alright, so the forces are different, distances are also different. So what will be the anti-clockwise moment here? Yes? Anti-clockwise moment will be due to which force? F1. And what is the perpendicular distance from the pivot? So what will be the anti-clockwise moment then? Moment of force means torque. So what will be the anti-clockwise torque? F1 D1, right? So F1 D1 will be the anti-clockwise moment. What will be the clockwise moment? It will be F2 D2. Okay, and my question is, when will it remain balanced? Like, when will it remain balanced like this? Not move here, not move here. When will it remain balanced? Remember, this is not a normal physical balance. This arm is longer than this arm. Okay, so when will it remain balanced?
So when F2 and F1 are equal.
Not really, Zishan, because if the two forces are equal, even then, because the difference in the distance, the torque will be different. So if the torque is different, it will cause it to rotate. Yes or no? Okay. So it will be in equilibrium when the anti-clockwise moment is equal to clockwise moment. You got it? Okay. So that it does not cause any rotation on any side. Alright. If anyone has a shop, okay, you can apply this cheating method. How can you apply? So imagine you have a physical balance. Just alter the balance, right? Instead of putting the hinge here, you put the hinge slightly on this side, slightly towards this side, right? Then let's say you have the pan balance of the same mass. You know, a normal eye will not be able to detect it. Okay. Now let's say that you put the weight on this side. Let's say you put 1 kg here. Okay. And here let's say you put less than 1 kg of the substance. Let's say here you're putting the block. Okay. And here let's say you're keeping, let's say you have a shop of potato. So you're keeping less than 1 kg potato. So depending upon the distance, this side won't the torque be more, even with less force, because the distance is more. Yes or no? Since the distance is more, to produce the same torque, you will need less mass. That way you can cheat very easily. Okay. So next time you go and they check with physical balance, just see whether the hinge is right in the middle or not. Because even if they move it a little bit here and there, they can easily cheat. Let's revise. What did we learn today from the beginning? We learned about
Translation motion.
We learned about translational motion, that is motion in the straight path. Then we learned about rotational motion, that is rotation about a given axis or pivot, right? Then we learned about torque. Torque is moment of force, which is given by force into perpendicular distance. Then we learned about
Couple.
couple. What is couple? Two equal, opposite and parallel forces acting around a pivot contributes a couple. And then what did we learn? Equilibrium. In equilibrium, what are the two types of equilibrium? Static and dynamic. For static, the body must be in the state of. For dynamic, the body must be in the state of motion. Very good. And then lastly we learned principle of equilibrium, a principle of moment, which says that in equilibrium, the clockwise moment must be equal to the anti-clockwise moment. Okay. So these are your questions.